This is Mr. Pillar, ECET 273, Modern Energy, lecture number 15. We're talking about alternate energy systems based on Unit 2 of the Fardo-Patrick text. We're just going to talk and touch on some alternative energy systems, and we're not going to talk specifics about them. The 5 sources we're going to look at, and we're just going to mention that they exist with brief talking about them. No real detail into them. Solar power, geothermal power, wind systems, fuel cells, and tidal energy systems. These are topics that are pulled out of the Fardo text, so I'm going to touch on them, and we will talk more about them in the lecture. Alright, so I've got a picture of a Rube Goldberg here, and I kind of want you to think about that. Current systems, we have complex energy transfers, and that's why we need to kind of talk about alternative energy sources, but specifically alternative energy sources that have direct conversion. Let's talk about how we produce energy right now with coal. So we burn coal, that heats a water steam system that then goes and turns a turbine. The turbine turns and rotates generator shaft. Generator shaft has magnets associated to it, electromagnet, permanent magnets, whatever. That magnetic field rotates along with the motor shaft. That field cuts through the conductors and through Lenz's law, Faraday's law, begins to flow current on the armature of that generator. So it's a lot like a Rube Goldberg. This has to happen perfectly, so that this has to happen perfectly, so this has to happen. We have phase changes in the type of energy. Okay, we have stored energy in the coal that then burns and heats and makes movement happen, which causes a magnetic flux changes, which causes current flow. All that loss. All right. Last lecture I showed the estimated energy use of 2011, and on that rate, out of that 97 quads, approximately 55 quads were rejected energy. So talking about alternative energies is great. Talking about the efficiencies of the energies is more important. We need to come up with some kind of way of direct conversion. And that's hopefully what we will evaluate some of these alternative energies on. Okay, a lot of these maps and drawings that I'm going to have are from the National Renewable Energy Laboratory. So this one is the beginning of that. This drawing that we show here, this map, is a map of the United States, the lower 48. And it's showing the kilowatt hour per meter squared per day annual capability of an area. So you can see high concentration of solar energy, and that's photovoltaic, flat plate, pointing to the south and at latitude. So what that means is the angle of the flat plate photovoltaic is at the angle of the latitude of the position that it's in. So we're sitting in Indiana somewhere around 45, 47, so we would have that angle on our solar panel, and we should expect in the green there we're looking at 2 to 2.5 kilowatts per meter squared. Down in the southwest we're looking at 7 to 7.5, and just kind of give you an idea looking at that. When we talk about solar power, your common answer is the photovoltaics, but I hope you reach back and think about the lab that we did. There was solar voltaics running that system, but the main energy that you were looking at was heating. So solar heat, like what we had in West Lafayette, or we could focus heat. What if you had a bunch of mirrors taking the sun in and focusing right towards a boiler and heating and steaming, and then going through the standard turbine, uh, steam turbine setup. So that wouldn't be a direct conversion. The solar heat of the propylene glycol to your next heating system, that would be almost a direct solution. Photovoltaics would be a direct solution. Those would be types of solar energies that we could utilize. Alright, so we are familiar with the solar. This is showing drawings and schematics on how geothermal systems could and do work. In the top right, you have, or I'm sorry, the top left, you have an injection well. So they drill down into an area just above a geothermic space, and they push water into that. Producing wells are where they would tap off steam that comes up and then runs through a standard steam setup. That is going down about 10 miles, and then each of those wells, the injection well and producing wells, another option, there's a place in California called Geysers, and that area is using a natural geyser, and the drawing on the bottom right is kind of showing that design. They have a pipe that's actually in the geothermal steam vent, and they're pulling that steam out. They do have these expansion loops that are marked on there. Those expansion loops are trying to catch the particles, rocks essentially, before they come into the steam turbine. And then they do a standard run. They condense it and push it back into the stream water above ground. And here again, two maps from the National Renewable Energies Lab. The top left are showing locations where there's potential deep enhanced geothermal systems. The dots are actually places that have power sources at. And the bottom right shows you the amount of energy that we create at specific states to generate power from geothermal. Now this is and this is by megawatts. These are talking about electrical production. This isn't talking about the geothermal wells that you would drill to heat and cool a home. This is actually pulling energy off of the mantle, the Earth mantle, to attempt to gain electricity. All right. As you can see, Indiana is fairly neutral, as you would expect. We have some warm spots, those orange areas there in the east, in the west. It gets more and more so as you go further and further west, and active. Up in the high mountains, well, there's not any activity. You can see in the far east, you can see basically the run of the Appalachians. Those are older mountains, and they're falling. In the Rockies to the west, it's fairly active, but those mountains are increasing in size as we go. So that kind of makes sense if you think about it in tectonic plates way. So this is actually a new idea to me, and didn't really think about it as an option before I was preparing this lecture, but I think it's worth talking about and looking at. Obviously it's working. There's a large number of facilities already in the western United States. Okay, so the National Renewable Energy Lab has a map that is a wind system. Talks about potential wind power across an area. Wind systems are AC/DC generators. The problem that they have is that there's no wind, no power. First models, and when we're talking about first models, this book reaches all the way back into pioneerish days. Fixed blades, high winds destroy the mill. They're even talking about mechanically using just to pump water. So they're really reaching back into a long time ago. Current designs have a variable pitch blade. It helps causing rotation for low and high winds, right? So if there's a little wind, if we can adjust the pitch of our blades on the turbine, we can catch that little bit of wind and get some rotation. Some rotation means some power. High wind happens, and it's getting spinning too fast. You can just completely pull your pitch to a flat to the wind surface, and it won't blow anymore, or it'll blow a lot slower. Let the fast wind go by. That would be damaging. I put the Indiana map on here for twofold reasons. I want you to see that it also has a overlay of transmission lines across the state. Those transmission lines are very important. If you think about it, just northwest of Lafayette, there's a very large wind farm. One of the problems they have, though, is they don't have any transmission lines to pull that power off. Those wind turbines were put up by a private group and not part of the local electrical supplier, and they're there. It's nice, but we can't bring that energy into the mainstream because we don't have a conduit for it. They're going to have to figure out how to get tied to those dark black lines, the 765 kV lines, to get really back into the system. Just a thought, just because you have energy there doesn't mean you can get energy to where it needs to be. Just another thought that we have to work on as we come up with alternative energies. So now we're going to talk about a fuel cell. And what is a fuel cell? Well, a fuel cell is a battery. It's nothing more than that. This isn't anything fancy, anything new. We've had these for a while. Fuel cells have powered space exploration for a very long time. They're ideal. The difference between a fuel cell and a battery is that a battery contains the fuel that will be consumed and then no longer be able to produce power. Fuel cell actually takes an input of hydrogen and oxygen, and that is what is consumed, and it turns into water, which is an ideal power source in space, because that water is then used for the astronauts to drink. So what's bad about them? There's catalyst that's required. I'm not a chemist, but essentially a catalyst is something that isn't part of the reaction, but its simple presence around the reaction allow the reaction to happen. The catalyst that is of easiest access right now is in short supply, as anything of worth it would be. And there's different catalysts. Some catalysts work at regular temperatures. Other catalysts need to be are only effective at warm temperatures. So you already have to put energy into the battery to get electricity out. Uses for this would be individual vehicle power, space, not really full scale to go into grid power. And I haven't been talking about this in the last few slides, but fuel cells do pass the direct conversion test, don't they? Wind turbines pass the direct conversion test. Geothermal is still back on we heat something to create steam, and then we go through the Rube Goldberg plan. But we're still, evaluating along the way on this. Now, I knew I was going to put in tidal energy, but I was really excited when I did my web search and found this. It's a little bit old. It's 2005. But Oregon State University had a conceptual of a wave park. This is pretty much close to a direct also. It has a buoy that will have a magnetic shaft anchored to the seafloor. The buoy goes up and down, the magnet stays in one location, but as the buoy goes up and down, it has coils that cut through the magnetic field. It becomes a generator. All that electricity is channeled back to shore. They're estimating this to be able to be 1.2 miles offshore. So how does that work? I know sitting here in Indiana, we don't really understand tides. But what happens is the level of the ocean shifts and over a large global scale. And so as I go up and down with the wave power, we get that because we've been to Michigan, Lake Michigan. But so imagine that in a large scale. You can calculate, you know when waves are going to go up and down. Basically, you know when a really wavy day is. It's a little bit of prediction, and we don't have full control over it. But they estimate that what they call a wave park, that's approximately 10 square miles, could potentially power the state of Oregon. The other benefit, some other tidal plans basically look like large dams. They're visible from shore. Their hope here was that it would be invisible from shore, and so it doesn't ruin the coastline view. So just something to think about. Oh, by the way, the buoys on this are estimated to be 15 feet across by 12 feet tall. As far as I know from my research that I've done thus far, it isn't something that they're doing right now, and like I said, the data that I was pulling out was from 2005, so it's been a while. But something to think about along the way. Now, I've always thanked the Fardo-Patrick text and the Square-9-DeWitt text at the very beginning, and I mentioned along the way the National Renewable Energy Lab, and I mentioned Oregon State. But I wanted to put those links here specifically so that you could see where I got my information on that. Hopefully you can pull some of those maps yourself. Again, take notes, watch the video again, and come to class with questions. Thank you very much.